Lagrangian mechanics is a reformulation of classical mechanics, introduced by the Italian-French mathematician and astronomer Joseph-Louis Lagrange in 1788. In Lagrangian mechanics, the trajectory of a system of particles is derived by solving the Lagrange equations in one of two forms. Either the Lagrange equations of the first kind, which treat constraints explicitly as extra equations, often using Lagrange multipliers, or the Lagrange equations of the second kind, which incorporate the constraints directly by judicious choice of generalized coordinates. In each case, a mathematical function called the Lagrangian is a function of the generalized coordinates, the time derivatives, and time, and contains the information about the dynamics of the system. No new physics is introduced by Lagrangian mechanics. It is actually less general than Newtonian mechanics. Newton's laws can include non-conservative forces like friction. However, they must include constraint forces explicitly and are best suited to Cartesian coordinates. Lagrangian mechanics is ideal for systems with conservative forces and for bypassing constraint forces, and some non-conservative forces. In any coordinate system, generalized coordinates can be chosen by convenience, to exploit symmetries in the system or the geometry of the constraints, which may simplify solving for the motion of the system. Lagrangian mechanics also reveals conserved quantities and their symmetries in a direct way, as a special case of Noether's theorem. Nevertheless, Lagrangian mechanics is important not just for its broad applications, but also for its role in advancing deep understanding of physics. Although Lagrange only sought to describe classical mechanics in his treatise Mécanique analytique, Hamilton's principle that can be used to derive the Lagrange equation was later recognized to be applicable to much of fundamental theoretical physics as well, particularly quantum mechanics and the theory of relativity. Lagrangian mechanics is widely used to solve mechanical problems in physics and engineering when Newton's formulation of classical mechanics is not convenient. Lagrangian mechanics applies to the dynamics of particles. Fields are described using a Lagrangian density. Lagrange's equations are also used in optimization problems of dynamic systems. In mechanics, Lagrange's equations of the second kind are used much more than those of the first kind. Introduction. Suppose we have a bead sliding around on a wire, or a swinging simple pendulum, etc. If one tracks each of the massive objects as a particle, calculation of the motion of the particle using Newtonian mechanics would require solving for the time-varying constraint force required to keep the particle in the constrained motion. For the same problem using Lagrangian mechanics, one looks at the path the particle can take and chooses a convenient set of independent generalized coordinates that completely characterize the possible motion of the particle. This choice eliminates the need for the constraint force to enter into the resultant system of equations. There are fewer equations since one is not directly calculating the influence of the constraint on the particle at a given moment. For a wide variety of physical systems, if the size and shape of a massive object are negligible, it is a useful simplification to treat it as a point particle. For a system of n-point particles with masses m1, m2, mn, each particle has a position vector, denoted r1, r2, rn. In three-dimensional space, each position vector requires three coordinates to uniquely define the location of a point. So there are three n coordinates to uniquely define the configuration of the system. Cartesian coordinates are often sufficient, so r1 equals, r2 equals, and so on. These are all specific points in space to locate the particles. A general point in space is written r equals. The velocity of each particle is how fast the particle moves along its path of motion, and is the time derivative of its position. Thus v1 equals dr1 dt, v2 equals dr2 dt, and so on. In Newtonian mechanics, the equations of motion are given by Newton's laws. The second law, force equals mass times acceleration, F equals md2r, dt2, applies to each particle. For an n-particle system in 3D, there are 3 n-second-order ordinary differential equations in the positions of the particles to solve for. Instead of forces, Lagrangian mechanics uses the energies in the system. The central quantity of Lagrangian mechanics is the Lagrangian, a function which summarizes the dynamics of the entire system. Overall, the Lagrangian has units of energy, but no single expression for all physical systems. Any function which generates the correct equations of motion, in agreement with physical laws, can be taken as a Lagrangian. It is nevertheless possible to construct general expressions for large classes of applications. The non-relativistic Lagrangian for a system of particles can be defined by where is the total kinetic energy of the system, equaling the sum sigma of the kinetic energies of the particles, and V is the potential energy of the system. Kinetic energy is the energy of the system's motion, and Vk2 equals Vk. Vk is the magnitude squared of velocity, equivalent to the dot products of the velocity with itself. The kinetic energy is a function only of the velocities Vk, not the positions rk nor time t, so t equals t. The potential energy of the system reflects the energy of interaction between the particles, i.e., how much energy any one particle will have due to all the others and other external influences. For conservative forces, it is a function of the position vectors of the particles only, so V equals V. For those non-conservative forces which can be derived from an appropriate potential, the velocities will appear also, V equals V. If there is some external field or external driving force changing with time, the potential will change with time, so most generally V equals V. The above form of L does not hold in relativistic Lagrangian mechanics, and must be replaced by a function consistent with special or general relativity. Also, for dissipative forces another function must be introduced alongside L. In the Lagrangian, the position coordinates and velocity components are all independent variables, and derivatives of the Lagrangian are taken with respect to these separately according to the usual differentiation rules. If t or v or both depend explicitly on time due to time-varying constraints or external influences, the Lagrangian L is explicitly time-dependent. If neither the potential nor the kinetic energy depend on time, then the Lagrangian L is explicitly independent of time. In either case, the Lagrangian will always have implicit time dependence through the generalized coordinates. One or more of the particles may each be subject to one or more holonomic constraints. Such a constraint is described by an equation of the form F equals 0. If the number of constraints in the system is C, then each constraint has an equation, F1 equals 0, F2 equals 0, Fce equals 0. Each could apply to any of the particles. If particle K is subject to constraint R, then phi equals 0. At any instant of time, the coordinates of the constrained particle are linked together and not independent. The constraint equations determine the allowed paths the particles can move along, but not where they are or how fast they go at every instant of time. Non-holonomic constraints depend on the particle velocities, accelerations, or higher derivatives of position. Lagrangian mechanics can only be applied to systems with holonomic constraints. 3 examples are when the constraint equations are non-integrable, when the constraints have inequalities, or with complicated non-conservative forces like friction. Non-holonomic constraints require special treatment, and one may revert to Newtonian mechanics, or use other methods. With these definitions, Lagrange's equations of the first kind are where k equals 1, 2, n labels the particles. There is a Lagrange multiplier lambda I for each constraint equation phi, and are each shorthands for a vector of partial derivatives, with respect to the indicated variables. Each overdot is a shorthand for a time derivative. This procedure does increase the number of equations to solve compared to Newton's laws, from 3n to 3n plus c. Because there are 3 n-coupled second-order differential equations in the position coordinates and multipliers, plus c constraint equations. However, when solved alongside the position coordinates of the particles, the multipliers can yield information about the constraint forces. The coordinates do not need to be eliminated by solving the constraint equations. In each constraint equation, one coordinate is redundant because it is determined from the other two. The number of independent coordinates is therefore n equals 3n minus c. We can transform each position vector to a common set of n generalized coordinates, conveniently written as an n-tuple q equals, by expressing each position vector, and hence the position coordinates, as functions of the generalized coordinates and time. The vector q is a point in the configuration space of the system. The time derivatives of the generalized coordinates are called the generalized velocities, and for each particle the transformation of its velocity vector, the total derivative of its position with respect to time, is given this vk. The kinetic energy in generalized coordinates depends on the generalized velocities, generalized coordinates, and time if the position vectors depend explicitly on time due to time-varying constraints, so t equals t. With these definitions we have the Euler-Lagrange equations. All Lagrange's equations of the second kind are mathematical results from the calculus of variations, which can also be used in mechanics. Substituting in the Lagrangian L gives the equations of motion of the system. The number of equations has decreased compared to Newtonian mechanics, from 3n to n equals 3n minus c coupled second-order differential equations in the generalized coordinates. These equations do not include constraint forces at all, only non-constraint forces need to be accounted for. Although the equations of motion include partial derivatives, the results of the partial derivatives are still ordinary differential equations in the position coordinates of the particles. The total time derivative denoted dt often involves implicit differentiation. Both equations are linear in the Lagrangian, but will generally be nonlinear coupled equations in the coordinates.